Hello there, this is exercise 2b. We're looking at graph theory again, and graph theory we started looking at in exercise 2a, so hopefully you've looked at that already. Now in exercise 2a we looked a little bit at what would be called traversable graphs, and you might remember the Leonard-Euler-Königsberg bridge problem. And I suppose this is similar to this kind of idea. Do you remember at primary school you got asked to draw this kind of shape? Oh no, I've gone wrong already. I was just drawing along there. So you're meant to draw this shape without taking your pen off the paper. If you can do it, you pass the test at primary school. And if you couldn't, then obviously someone else would show you how to do it. And of course, the way to do it is, I suppose, you may remember this yourself. So if I just have a go at this. There. Yeah, I've done it this time. And I did manage to do it. I managed to traverse the graph without taking my pen off the paper. Now, graphs which are called traversable, also, we're from now on going to call them Eulerian graphs. And an Eulerian graph is one that you can traverse without taking your pen off the paper. You can draw it all. Now, we talked a bit about this last time, that if there are odd nodes, odd vertices, then that will make the graph either traversable or not traversable. Now on this one, I'm just looking at the degrees of this one. That's a 1, 2, 3. This is a 1, 2, 3. 1, 2, 3. That's a 4. That's a 4 as well. And this top one's a 2. So you'll notice here I've got two odds. And because it's two odds, you may remember this means it is semi-Eulerian. And a semi-Eulerian one means you can draw it. Yes, you can traverse it, but you end up in a different place to where you started. If there are no odds, it's what we call fully, I've just realized, zero odds. This is fully Eulerian, and that means you start and finish where you left off, and you can properly do it. But if you get 4 or more, then we call this neither. It's basically you can't traverse it. And this is something we talked about right at the end of our exercise 2a. So if I just look here, I'm just looking at so this is a 2, and presumably therefore this is a 2, a 2, a 2. So I don't need to worry about any of those. Now what's this one? 1, 2, 3, 4. That's a 4. And that's a 4 there as well. So I think there are no odds. So I think A can be traversed. B, I'm just looking at this. 1, 2, 3. I think that's a 4. And I think that's a 4. And that's a, I think these are all 4s. Now you just got to get your head around it. 2 there. Yeah, I think so. This is okay. Now this one, what's this? The middle one, by the way, is a 4. 4, 4. What's that one? 1, 2. That's a 3. And I think these edge ones are 3s. I think this one has got 4 odds, so I don't think this is traversable. What about this last one? So that's a 2, a 3, and a 2. So I think that's got a 3 there and a 3 there, but the others are 2s. So I think this is semi-Eulerian, but it is traversable. So I suppose the number of odds is what I want you to, A, B, and D. Yes, I agree with that. So the number of odds is what matters, and this is the notes, I suppose. An Eulerian graph has no vertices with odd degree, or no odd vertices. A semi-Eulerian has exactly 2 with odd degree, and if it has none, then it's not traversable. Describe these as Eulerian, semi-Eulerian, or neither. Well, let's just count the degrees of each one. So this is a 2. These are all 2s. So after the difficulty of even seeing that last picture, this is suddenly dead easy. All even numbers, so this is Eulerian. And what about the next one? Well, this is a 2, this is a 1, 2, that's a 3, 2, 3. All right, so it's got 2 odds. So I think this is semi-Eulerian. Let's see what they reckon. Eulerian and semi-Eulerian. So at least we agree. Now, having done that important idea about Eulerian graphs, now we're going to look at what are called isomorphisms. And an isomorphic graph is one that, or rather two isomorphic graphs are basically, they are the same graph. And you've got the Greek there if you're interested. But basically you can redraw it from one version to the other and it's essentially the same structure. Now, one way of trying to justify that two graphs are isomorphic is to be able to link up the vertices on one to the other graph, and this is the set by setting up a correspondence between the vertex sets. So if I have a look at this now, which one's which? So the one way to do it is to look at the vertex degrees. That's a 3. This is a 3. This is a 3, and this is a 3. All right, so they're all 3s. Oh, in actual fact, I'm just realizing here, if I was to draw that line straight across instead, then it actually looks exactly the same as this. I didn't realize that until I looked at this picture. So you can just then go, W is kind of equals the A, and you can say that Y is equal to the C, and you can say that X is equal to the B, and you can say that Z is equal to D, and therefore isomorphic. That would be the way I would do it. Let's have a look at the next one. It says set up a correspondence between the vertex sets, and that's exactly what I did. So what's this next one say? Show that these graphs are isomorphic. Can I do it in the same way? I'm going to look at the vertex degrees again. This is a 2, 1, 2, 3. This is a 4. This is a 2. At least they're not all the same this time. 1, 2, 3, 4. This is a 2. They're either 2s or 4s. I suppose the key thing is here, we've got a 4 and a 4 either side of each other. And these are the 4s down here. 1, 2, 3, 4. Yeah, there they are. And then the 4, there's kind of a 4, a vertex. This W is in between the two 4s. What's that? Oh, I see. That's like a W, and that's like an X. And therefore this presumably is like a U, and this is like a Z. So again, by setting up that correspondence, and they've looked at vertex degrees, but they said U equals A. They've done exactly the same as me. Z equals A. Yeah, I think I've done exactly the same as them. So this is correspondence, and that hints at this idea of degrees or orders of a vertex. And it's very common to write out what's called a degree sequence, where we did a bit of this in exercise 2a. So for instance, draw two non-isomorphic graphs that each have this. All right, so this degree sequence then. So I've got to do 1, 2, 3. I've got 4 1s. So I'm tempted. I don't know what this is going to look like, but I'm tempted to put those on the outside. Then I've got this one in the middle. It's going to 4, but I'm kind of thinking, how about something like that? Because that would be a 2 and that would be a 2, and then I've got 4 1s. Is there another one? It does want 2, so I'm kind of cheat. So there's my. Oh, I see. They've just moved this bar effectively 1 over, and it's exactly the same scenario. I found this one, but you'll notice if I'd spent longer on it, I'm sure I would have found that one as well. But notice although they're non-isomorphic, because the bar effectively shows you, it's a bit like chemistry when I look at those pictures in chemistry of two different organic compounds, and you're meant to say if they're the same or not. Here you can see they're not quite the same, and the numbers of the degree sequence might be the same, but you can see that the degree sequence in itself isn't enough to say that they're isomorphic. It might be enough to show that they're not isomorphic, but it's not enough to show that they are isomorphic. So just bear that in mind. Planar graphs, and again, this is another idea that we touched on last time. So we're just trying to build up your skills and your language of discrete graphs. Some graphs look the same but are not isomorphic. Well, we've already seen that. For this reason, and to avoid ambiguity, we sometimes try to draw graphs without any arcs crossing. And you can easily do that in terms of, if I had, for instance, that one there, and this one then comes across. Now, it looks in the middle as if that is a vertex, and it's not a vertex. It goes above it. So one way of avoiding that problem is to draw the last arc going around the edge of the graph. And you can see now they are joined. It's like there. Now, when you draw them like this, it's a bit confusing. This is definitely therefore a better way of doing it. And once you've drawn it like this, you can easily see it's planar. So a planar graph is any graph that can be drawn with no arcs crossing. And this idea it's only one layer or thickness is an important one. And we come back to that in the future. So look out for planar graphs and whether graphs are or are not planar. So I've got an example of this here. It says a simply connected graph is drawn on 6 vertices, and I've drawn the 6 vertices for you here. The graph has a maximum number of arcs. This reminds me of a K6 graph. And we saw last time that K6 graph basically has 6 dots where you join them up like so. And you draw into all the other points, and then I go from here. I draw them to all the other points. And this one, because it's already got some drawn, you soon realize you don't need as many lines for these. And this one probably just needs a couple. And this one, so that's a K6 graph. But look, the suggestion is then, now how many have I drawn there? I had a formula last time. It was n minus 1 over 2. And that is 6 times 5 over 2 is 15. I don't think I'm going to end up drawing the maximum possible number of arcs. My suspicion is it won't be planar if I do that. So let's see what I can do. Let's see if I can draw this. Let's join all those up. That can go to there. That can go to there. I want to draw this almost like this. Oops, missed, but you get the idea. Now, can I draw any more? Well, definitely I can. That one can definitely go over there. Can I draw any more? That one's good. I'm definitely kind of blocked off here. Let's see what my answer actually is. Oh, that looks very similar. I drew from there to there. They've drawn instead from around there to there. But you can see that's what I ended up with. How many lines was it in the end? 1, 2, 3, 4 on the top. 5, 6, 7, 8. It was actually only 9 arcs in the end was the maximum. And my K6 graph had 15. So you can see it is, to be planar means no lines crossing if we're only going to draw this with thickness 1. And I've just got a little note to you here. A planar graph can be drawn like this. This may appear to be non-planar, however, it can be redrawn. And this is what I was showing you before. In fact, it's the exact same example, just drawn a different way. Now, bipartite graphs, let's have a look at these. Now, we've already seen K-graphs, complete graphs. A bipartite graph is where you've got one set of dots or vertices which are joined to another set of vertices. But notice none of these are joined together and none of these are joined together. So this is a bipartite graph, but it's not a complete bipartite graph. Let's draw a complete bipartite graph. Basically, that one is drawn to both of them. Over here, you notice again I've got one set of dots here, one set of vertices, another set here. That vertex is not allowed then to be joined to these 4 over here. So, but this one has to be drawn because it's complete to those 2. This one has to be drawn to those 2. And I've got this one has to be drawn to those 2. And you'll notice this is called a K4,2 complete bipartite graph. 4 dots on this side, 2 on this side, and this is a complete bipartite graph. And we're going to have a quick look at this example. And we've got here 5 people even, if I wish I could count: Asha, Brian, Callum, Darshana, and Elizabeth. You can see A, B, C, D, E, and then there's some subjects they can take. So I suppose what I'm going to do is I'm going to have the 5 people, and over here I'm going to do the subjects. So I suppose I need to just write the A, B, C, D, E here. Now, these 5 students there, what's a dodgy D? And these 5 students then can't obviously be joined to any of them each other. But what they can be joined to is the subjects they teach. So what have we got? We've got physics. Well, I'm going to call that, don't know how many I've got over here. But 1, 2, 3, 4, 5. I think I've got 6. So 1, 2, 3, 4, 5, 6. And I've got physics. I've got chemistry. I've got maths. I've got psychology. I've got German. And I've got sociology. Oh, that one was meant to be an H. I'll better make it look like an H. So let's just join them up now, and then we'll have our bipartite graph. And you'll notice this is a real-world example of where a bipartite graph might be useful, but you can also get the questions which are just, here is a bipartite graph, now just do something with it. So anyway, Aisha takes physics and chemistry. Brian takes chemistry, maths, and psychology. Callum takes psychology and German. Darshana takes German and sociology. And Elizabeth seems the clever one. She's doing physics. Look at that. Sociology. Chemistry. And German. She's just showing off, isn't she? But you can get the idea of that group of 5 students, and that's a bipartite graph to show all that. So here's another part of bipartite graphs, and I suppose it comes back to this idea of complete bipartite graphs. And we had a formula for this when we were doing complete graphs as well, and I've shown you that already in this video for KM. So let's have a look. So if I had, I'm just making this up now, if I had 3 here and 2 here, you can see that's 1, 2, 3 to that one. And for this one, we've also got effectively 3 as well. And you'll notice, actually, we've ended up with 6. And that makes me think, on this case, it's 3 times by 2, which gives me 6. And in actual fact, I think this formula is just PQ. If I have 4, 2, like I did last time, I think I should have 8 connections. 1, 2, 3, 4, 5, 6, 7. Oh, I've just realized this is not a K42. This was my K42. 1, 2, 3, 4, 5, 6, 7. That makes more sense now. And if it's not complete, of course, it won't follow that rule. But if it is a KPQ graph, then it should be just equal to PQ, which is what the answer says. So we're going to have a look at our textbook in class will be this exercise 2B from this Cambridge textbook. Thank you very much.